And we are back, second hour here, Wednesday, July 8th, part 2 now. Quiz 4 due tomorrow. Should be able to cover most of those reactions. If we don't cover all of them, you can read ahead and get a little help in recitation maybe. We should get to them though, the Grignard reactions, cuprates, whatever. Homework 5 isn't due till Friday, and we'll start 21 there. So just to summarize here on the upper board then, we see a lot of, so switch the view up here to up above. Ruben, are we seeing that? Okay. So, we've been mainly working with LAH and sodium borohydride, well, all of these. We covered all of these right now. So the universal reducing agents LAH. So all these different things go to all these different products. These all make sense now, what we've covered mechanistically, but not this one, the amides. I'll say a little bit about that on the board here. Those go to primary amines, okay? All the rest go to alcohols, okay? Secondary alcohols, ketone, but all the others, the derivatives and the aldehydes, all go to that. We got sodium borohydride specific for aldehydes and ketones, okay? And then the milder reagents here, the tri-TP-toxyaluminum hydride and dibol go to aldehydes. So let's look at that last one briefly here. So if we go over here to the board, Ruben. So we got carboxylic acid, yeah, down to the primary alcohol. And that's because you can deliver 2 hydride reagents there. And eventually, the oxygen winds up on aluminum. The mechanism's kind of complicated there. The key thing you need to recognize, though, is, the hydride reagent adding to the carbonyl. And then the tetrahedral breakdown to an aldehyde, and then further reduction to that. Now, this is a little bit different here. Mechanistically, we're going to end up adding a hydride there. But you see, we have the aluminum with more hydrides on it. And we have the first hydride added. Then we have an amine like this. Now this amine here, you see, can actually force off the aluminum oxide. And you have to adjust the hydrides there, but you get this type of intermediate. And we'll see this later on. This will be an aminium ion, you see. And then the next hydride can add in here, and then you go to the amine. So I'm not showing the full mechanism. I've never put it on a quiz or a test, but it's a similar thing, except for this part here, where instead of breaking off the nitrogen as leaving group, the better leaving group is actually the aluminum oxide, because aluminum and oxygen bonds are very stabilized. So when the tetrahedral intermediate gets here, actually the lone pair of nitrogen pushes off the aluminum oxide. You get this aminium ion, and then the second hydride adds there. So both these hydrogens again come from LH, but I won't go through the full mechanism, so don't worry about that. All right, let's review oxidation of alcohols briefly, because we have already covered it in 351, chapter 12, if you need to review this. So if you have an aldehyde, for example, you can oxidize that with chromic acid, okay? Or potassium dichromate and sulfuric acid, whatever. The chromate, though, is the strong oxidizing agent. Goes all the way to carboxylic acid. And you can use the aldehyde, or you can use the primary alcohol, right? All the way to the carboxylic acid. Ketones with this reagent go to what? I'm sorry, secondary alcohols go to ketones, okay? Stops at that point. So in order to keep oxidizing your secondary alcohol, you'd have to break carbon-carbon bonds. And remember, tertiary alcohols don't react, okay? So you have to have a hydrogen on there to take off in order to do the oxidation. The mechanism, you don't need to know that. Okay, we have another reagent here, and this is a new reagent. We'll see it more in sugar chemistry. It's a milder reagent. So here we got an aldehyde with an alcohol here that could get oxidized, right? But this new reagent will be silver oxide. That's Ag2. Why is that silver? stands for the Latin argentum, right? Argentina, the silver country, maybe. That's how I remember it, AG. Okay, silver, argentum, the periodic table, that's silver. Silver, there's two of them on each oxygen, so that's in the silver 1 oxidation state. And usually it's added with some base, either ammonia or hydroxide is added in there. And, there's water, of course, in there. And it's a milder oxidant than the chromium. It will just oxidize the aldehyde and leave the alcohols alone, okay? It's kind of a neat reaction. The byproduct is actually silver 0, which is the reduced form of silver. It'll form a silver mirror on the flask. We'll see this later on in sugar chemistry. This is the so-called Tollans test for aldehydes. Any aldehyde will work with a silver oxide. If there's anything else in the molecule that can oxidize, it won't, okay? It'll just oxidize the aldehyde. There's one other reagent here. It was PCC. You remember what that stands for? Not the Polynesian Cultural Center, okay? Even though you'd like to be in Hawaii right now. PCC stands for Pyridinium Chlorochromate. This one does not have hydroxyls on the chromium, and the chromic acid has water. This can be done anhydrous here, and it will stop at the aldehyde, okay? And that's a very useful transformation. We saw that in chapter 12. That's good to review it now. These are all oxidations, right? We're adding more oxygen to the substrates. Selective oxidation here on the more susceptible aldehyde, going to carboxylate without bothering the alcohol with the silver. That's the only new one, okay? So don't worry about that. And nothing on the mechanism there. All right, let's get on to the main event here. Some people call this the most important organic process here because of its versatility. Now, I already told you the Friedel-Crafts was considered one of the most important industrial processes ever. This one rivals it, though, I think, the Grignard reactions, the ability to form carbon-carbon bonds now and make all sorts of different products. So the Grignard reactions are going to be very important. These all have to do with organometallic reactions, okay? And by organometallic, we mean a carbon-metal reagent here, okay? And we have a metal bond here. We'll see lithium, magnesium, and copper reagents. And the nature of an organometallic bond is such that what? If we consider the resonance form here, it's carbanionic. Why? Because the metal is less electronegative, right? They're very electropositive, being on the left side of the periodic table. Carbon, even though it's not very electronegative, 2.5, what metals are down, 0.9, 1 or so on the Pauling scale. So you see, these electrons are actually polarized toward this, and that will be our nucleophile now, okay? So they're basic, they're reactive. If you have any water available here, they will protonate right away and form alkanes. We need to keep water out of the reaction. We'll say a little bit about solvents. We'll use a solvent called THF for tetrahydrofuran. And this cyclic ether here is a very good solvent. It's a liquid, and it can coordinate the metal and make the organometallics more reactive. But it's aprotic. There's no protons here. We keep water away from them. Why? Because water would just grab the proton off the strong basic thing and make the alkane, okay? So that's the basic idea. Now, the reactions we've seen before, reactivity with carbon, were this, right? Where we had a more electronegative halide, bromide, chlorine, whatever. And here the polarity is such that what? We were thinking of carbon as an electron deficient species with a halide leaving group. So here's all your SN2, SN1, E1, E2, whatever, where the carbon, because of a leaving group that's polarizing electrons the opposite way, was more electron deficient. Now we're thinking about organometallics as the carbon being the electron-rich species. So it's kind of a paradigm shift in your thinking there. But this unifies now the topic here in 352 with the topic before. We've changed the polarity of this carbon substituted bond here, okay? And the reactivity with the lithiums and the different reagents. So we'll have different reagents. Let's do a little bit on the naming of these. And we won't do complicated names, but you should be aware of what they are. So how about methyl lithium? And lithium is monovalent. It's the first row, alkaline earth, alkali metal. So it's just monovalent there. So we just call that methyl lithium. Okay. And that's usually how they are, alkyl and then the name of the metal. Okay. A little bit different though on some of these here. Oh, how about this one? So that would be vinyl lithium. Okay. In the vinyl group, maybe you should be familiar with there. You can name some other organometallics. This would be allyl potassium. Okay. We're not going to do organopotassium reagents, but that's how you would name that one. You can have then an alkyl group on magnesium. And because magnesium is divalent, it's an alkaline earth here, we have a halide and an alkyl. You can have the dialkyl magnesium, but these right here are actually the Grignard reagents. Okay. And I should say something. I'll show you Victor's picture here. This is a person, French guy, won the Nobel Prize, Victor Grignard. And don't say Grignard. That's not how you pronounce it in French. It's Grignard reaction, Grignard. Okay. When you take care of your yard at home, you want to keep it green. Okay. Don't mispronounce it. But that's not the common name. We call these Grignard reagents, but what would we call this? Ethyl magnesium, and the halide. This is bromide. Okay. So yeah, that's ethyl magnesium bromide, or the ethyl Grignard reagent. Okay. And then we got one more here, the copper reagents. Let's have diethyl cuprate. So yeah, these are dialkyl. In this case, it's diethyl lithium cuprate. And these are kind of funny, right? Because we have two metals there, the lithium and we have the copper. So we'll have to look at that structure a little more carefully. Two metals together. Well, actually, the two alkyls are on copper, and overall, the copper has a negative charge. That looks kind of funny, doesn't it? A metal with a negative charge. Oh, have you seen that before in formal charges? And the lithium is actually cation. But that's the name, dialkyl lithium cuprate. Okay. To give that search. So those are the ones we'll be looking at here for reactivity. All right, so let's see, which one should we start with first? Okay. Yeah, well, let's just jump ahead. Okay, so let's look at the Grignard reagents. Well, I don't know. Let me show you the lithium reagents too. You take lithium here, two equivalents of the lithium, and you form the alkyl lithium plus some lithium chloride. So that's where your two lithiums wind up. And lithium is monovalent, so it's got to react there. And the real driving force for it is the formation of the metal halide, which is a stabilizing thing. In fact, that's a solid material. As that precipitates out, that can drive the reaction. You can purify that away from what you want there. You do it in ether or in THF, and you can't do it in water. You've got to have it anhydrous away from the water. So let's see for a Grignard reagent. And you can do the halide, any of the halide, chloride, bromide are best. Fluoride's unreactive. Iodide is reactive. You can use iodides. It can be sp3 hybridized, the alkyl, or it can be sp2. It can be vinyl or aryl. And it can be primary, secondary, or tertiary here. But it also can be sp2 for that group there. And like I said, chloride and bromide are the most common ones. So we have magnesium metal in THF. And we start out with the metals, the shiny stuff, the reduced stuff here. And we get to the ethyl magnesium bromide. Okay. And what you can say here, looking at the oxidation state, the metals start out in the zero oxidation state. That's the shiny metallic stuff. But now we have the metal here, the magnesium, bonded to two anions, right? So what's the oxidation state of the magnesium there? Yeah, it's in the +2 oxidation state. In fact, sometimes this is called an oxidative insertion mechanism. I'm not going to go through the mechanism of it. It's actually a multi-step radical mechanism where you move one electron at a time. The magnesium has 2 valence electrons on it, being in the 0 state. You transfer 1 electron to bromide to form a radical anion that fragments. Yeah, don't worry about the rest of that. But this has to be in solution, right? Ethyl magnesium halide. Now, the key reaction is, in the second step, we add a carbonyl compound, okay? So this is the Grignard reaction now. So here's our carbanion. Let's have it act as a nucleophile, push the electrons up there. And what? We get the ethyl group down there. Oh, now minus, where's the magnesium end up? Well, it's right here. Magnesium bromide plus charge, okay? We could draw that as a covalent bond right there. Doesn't matter. Oxygen and magnesium are very different in electronegativity. It's okay to draw it as an ionic state. You see, here's the nucleophile that just came off of there as a carbanion. Now, there's a second step here, which is water. Why do we have to have the water? We're quenching it, just like we did the hydride reagents. The alkoxy groups takes the proton off there. And what? We get the alcohol product. And we get magnesium hydroxide. You don't need to worry about the magnesium hydroxide. When we do the extraction, we get the alcohol product, okay? Now, this is the key thing. Let's look at a number of reactions here and the versatility of the Grignard reagents. So let's take our diethyl magnesium bromide and react it first with formaldehyde, the simplest aldehyde, right? What do we get here? Well, we get the ethyl group on there, O minus, and there's only the 2 hydrogens there, right, from the formaldehyde. And then quench with water, and what do we get? Yeah, the primary alcohol. Okay, so we can always take the Grignard reagent, which we got from the alkyl bromide, react with magnesium, turn it into a nucleophile, and add another carbon on there. We went from a 2-carbon ethyl bromide to a 3-carbon alcohol. And what type of alcohol? Primary with formaldehyde, okay? That's a very useful reaction on its own. But here's why Victor won the Nobel Prize. It's very versatile. What if you take an aldehyde now, okay? Not just formaldehyde, but an aldehyde with a carbon on there. Right, so we'll add our ethyl group on there, and we still have this methyl group from the original aldehyde, right? We just made that bond right there. And now we quench with water again, and what do we get here? Yeah, we get the secondary alcohol, okay? So we can convert any type of alkyl halide, sp3 or sp2, into secondary alcohols with aldehydes. That's not the end of the story, though, right? We can take ketones. And now let's add kind of a more complicated ketone here, right? And let's see. We've got this ketone with our ethyl magnesium bromide here. What are we going to get? Well, we're going to get ethyl ketone there with another ethyl group on it. And now we're going to quench with water again. And what do we get? Yeah, we get the tertiary alcohol, okay? So notice the versatility there and what we're able to do, okay? We can make any of these products from a simple Grignard reagent, the alkyl magnesium bromide. Okay, this relates to the other organometallics. Let's see if we can do a couple here. Let's take, benzaldehyde, and let's react with what we just did there. Let's do our alkyl magnesium bromide and then quench with water, okay? But let's also take vinyl lithium and also quench with water. And let's take, sodium acetylide, which we learned before in 351. Can you come up with the 3 products there? You can pause your video and work on those. Okay, we're back here. Let's see what we got. Well, we got our benzene ring, and that's a phenyl group. I'll just abbreviate that. And what should that be? Well, the ethyl group's on there, and it is an aldehyde, so this should be what? Yeah, a secondary alcohol. And there it is. We just made that bond there. Here's where our aldehyde was. The benzene's there. Secondary alcohol after quenching with water, right? And we get that. What about with the lithium? Well, it's also nucleophilic. And then if we quench here, we'll get also secondary alcohol, but it will be a vinyl group on there. So there's our group we just added on there, okay? Now we could have done that with a vinyl Grignard also from vinyl bromide or vinyl chloride. But sometimes these are easier to make, the lithiums. I showed you how to make them there, but yeah, don't worry about that. This one we know how to make. This one, we take simple acetylene or any terminal alkyne, right? And we treat it with sodium amide, right? Or sodium hydride. And that's because those bases are strong enough to pull a proton off. The pKa here is what? 25, right? And the pKa of ammonia is 38. So we're going in favor of the weaker acid there to take that proton off. So we can add this and add that in there. And what do we get? We get the alkynyl alcohol. But notice these are all secondary, okay? But just with different nucleophiles added on there. So don't forget about the acetylide reactions. They're similar to the alkyne reactions in that case. All right, so any of those reagents can react with aldehydes or ketones. Formaldehyde, primary, aldehydes, secondary, and if we have ketone with any of these, right, we get tertiary. So a broad range of reactivity there. What about esters now with Grignards? So here's an ester with an ethyl group here, ethyl propionate, and let's add methyl Grignard here. Methyl magnesium bromide, we make that from methyl bromide and magnesium metal. We react it here, we quench with water. We use excess. If we just use one equivalent, we'll get a mixture. So with esters, we have to indicate an excess. And we'll either say EX or we'll put two equivalents there, okay? And if we do that, what do we get? We get the alcohol, but from an ester here, with excess Grignard, we get the tertiary alcohol. So how does this work? Well, let's go ahead and do our nucleophilic attack, just like we did before. O minus. This will give this, right? There's our tetrahedral intermediate. That can break down now, right? We can push this off. Why? Because oxygen's electronegative. This bond is weaker than a carbon-carbon or carbon-hydrogen bond because of that. Plus we have the magnesium cation that can help ionize that off, okay? We'll see what the intermediate looks like. It's going to be what? A ketone, right? Plus we'll have the ethoxy group on the magnesium, okay? So metal-oxygen bonds are stabilizing. That's another reason why the tetrahedral intermediate breaks down at that point. How do we get to this product then? Well, we've got excess of the reagent, so we can add another equivalent, right? And what do we get? O minus again with that. And some more magnesium bromide salt there. And what? That looks like the product. What do we need to do here to finish off the mechanism? Yeah, just quench with water. And remember, that's a second step. So that will form some magnesium hydroxide, and it'll form the tertiary alcohol in this case. So here's a case where what? We have a Z group, which is a potential leaving group. Why? Because of the relative weakness of this bond and the ability of that to be electronegative to then interact with magnesium and come off, okay? So normally with the aldehydes and ketones, the tetrahedral intermediate was just directly protonated. Now with the ester, we get that type of reactivity. What about acid chlorides? Can you make a prediction there? Let's look at an acid chloride here. How about benzoyl chloride? It's the acid chloride from benzoic acid called benzoyl chloride. And let's add ethyl Grignard, two equivalents, and then quench with water. Work on that product. See if you can get it. And we're back. We'll have, yeah, this alcohol. That's where the carbonyl was, right? But we have a leaving group, the chloride, And what? We're going to put on 2 ethyl groups now, right? So we'll make the tertiary alcohol, and these 2 groups came from the Grignard reagent. Okay, let me give you another problem to work on. Let's look at this the opposite way. Can you make this complex alcohol using organometallic? What are we going to do here? And what's your starting material? That's a good one to think about. So tertiary alcohol, you have a few options there, actually. There are different ways to approach this synthesis problem. But pause there if you like, work on that. Okay, and we're back. So you can analyze this and say, well, I can make any of these bonds from Grignard reagents. Let's make this last bond up here. So we'd have to start with this ketone and what? And methyl magnesium bromide. Okay? And that would indeed make that product there. Okay? That's pathway at the top. What about this pathway here? Well, then we'd have to start with this ketone. Oh, that has a name, right? That's acetophenone. And how would we do it? Well, we'd have to put on the vinyl magnesium bromide, okay? And that would give that one. Is there another way to do this? Yeah, we could start with this ketone. We could start with methyl vinyl ketone, MVK it's called. And what? We'd have to react with phenyl magnesium bromide, okay? So it'd be ways to make each one of those. Which one's best, do you think? Well, you'd have to look up the prices of each one of these and maybe try the reaction. And that's what we do in the lab, research. We look into different pathways. I know the cheapest one, and that's acetophenone, okay? This vinyl phenyl ketone is actually kind of expensive. We'll show you how to make each one of these. Well, you already know how to make that one, right? From benzene. Acetophenone, ferrocross acylation. Vinyl mag bromide is cheap. Can react that, quench with water. I'm leaving out the water quench, and I'll get to that. This one's also pretty cheap, methyl vinyl ketone and phenyl Grignard. Let's see, how do we make that one right there? Let's say we got this top pathway. How do we make this ketone here? Well, we'd make the ketone from this alcohol. And what reaction do we do there? Yeah, oxidation. We could use PCC or the chromic acid. Okay? Oxidizing secondary alcohol to a ketone. Once we have an alcohol, then we know how to make that. What type of alcohol is it? It's secondary. So yes, of course, we can use a Grignard reaction here. There's a couple we can use. The cheapest one is to use benzaldehyde plus what? Vinyl magnesium bromide. And of course, we quench with water. But both of these reagents are relatively cheap. We'd make that, and then make that. So it'd be like a 3-step synthesis of that. We're showing you how these reactions can be used sequentially there to do different types of reactivity. All right, let's look at acid chlorides with Grignards. We'll go back up to the board or the overhead in a second here, but I think we can cover some of these here. Acid chloride with, let's do isopropyl magnesium bromide and quench with water. And we're going to use excess, 2 equivalents. And we'll specify that if we mean that. And that should alert you to it, right? This is a derivative carboxylic acid. So if we use excess of the Grignard, what are we going to get here? Well, we're going to get the tertiary alcohol. And what? The 2 isopropyl groups on there. Okay? You can see the complexity of these building up here. To review the mechanism briefly, what we get to the tetrahedral intermediate, O-, Cl, and isopropyl. Now, before we just quench there, but what do you have here? You got an even better leaving group than from the ester, right? So this can break down. This will wind up on magnesium, and you will get a ketone intermediate. So you need to be careful of this. The esters and the acid chlorides add 2 times the organometallic. And then what? This is just more Grignard adding. Push the electrons up and then quench. So that gives the second one added on there after we get the first, okay? So yeah, I think that's a good way to go there. Okay, let's look at another reagent here, and that is the acid chlorides again, but let's look at the cuprate. Now, I haven't shown you everything about the cuprate, but you can see what it is. It's two alkyl groups on copper, which is negatively charged, and the lithium. And if we do this with an acid chloride, look at the product you get here. It stops at the ketone. It just adds once. This is far less reactive. This is a milder reagent than the Grignards. The Grignards are from magnesium, right? Those are alkaline earth metals, which is the second row, very electropositive. Where's copper in the periodic table? I think you can remember that. It's at the end of the transition metal series. It's in the middle of the periodic table. It's not as electropositive. Copper reagents are not as reactive. So it's not reactive enough to add in here. It's only reactive enough to add once. And then when it gives that tetrahedral intermediate, the chloride stops there. And even if it breaks down during the reaction, the cuprate doesn't have enough nucleophilicity to add to a simple ketone on its own. So it stops right there. But it does go through the same intermediate here, but just recognize this is a later transition metal and it's less reactive, it's milder. All right, and we'll get to enones here in a second with cuprates also. Let's see, can we react Grignards with CO2? Carbon dioxide. We just draw it like CO2 before, but here I'm drawing it as a carbonyl, so you can see this, right? How do these react? Well, here's our Grignard reagent. Let's push the electrons up there. Here we get our benzene on there, and what? We get O minus here, okay? Oh, that already looks like a product, we know, right? The second step here is adding some dilute HCl. And we do need something that's a little stronger acid in this case, because what? We're protonating a carboxylate. We want the neutral carboxylic acid. The pK of that is what, 4.4 or 5 for benzoic acid. 5's the number you need to remember. So as long as you have a dilute acid here, you can make what? Carboxylic acids from Grignard reagents. So this right here, any Grignard, any R group, you see can go on there on CO2 and make the corresponding carboxylic acid. So you can see why Victor Grignard won the Nobel Prize. He opened up the synthesis of all sorts of other functionalized molecules and clearly created a very versatile, useful process here. Let's see, is that the end of the story? No. You can take Grignard reagents. Let's take this one, N-propyl magnesium bromide, and react it with this electrophile. What's that? Epoxide, right? Or ethylene oxide. Let's see, how's this going to react? Ethers normally are unreactive. In fact, usually we do the Grignard reagents in ether, in THF, the cyclic ether. That's the solvent. Here we're adding another cyclic ether, epoxide. Well, that shouldn't react. Yes, it does, okay? After we quench with water, guess what we get here? We get the primary alcohol that has 2 extra carbons in it. Here is our propyl group. We just made this bond. 1, 2, 3, 4, 5 carbons. What's up with this? Well, obviously we added 2 more carbons from the ethylene oxide, from the epoxide. How? Well, we have strain in the small ring, right? This is constrained to be 60 degrees for the bond angle there. No, this is sp3 hybridized. It wants to be what? Wants to be 109.5 degrees, right? But because it's constrained in this ring, it's very reactive, much more reactive than THF. THF is inert to these reagents. It just helps solubilize these, bring them together. We only bring in water at the end, again, to quench, but what's the result here on the mechanism? So we'd have this bond being formed. We'd have O minus here. So this is the 2 carbons. We just made that bond right there. And then what? When we quench with water, we're just protonating to give that. So this is a way to 1 carbon extend Grignard reagents. Okay. What if we have an epoxide like this? And we have a Grignard reagent. Oh, let's do vinyl magnesium bromide with this one and water. See if you can do that one. Which side of the epoxide are we going to react on? Are we going to react on this side, the quaternary side, tertiary side, or this side, which has what? A primary position. And what? This is a charged, strong nucleophile. So that should tell you it's going to go after the less substituted end. Why? Because it's a bimolecular reaction. It's like the SN2. It's going to want to prefer adding to the less hindered side. Not here. It's going to add there. And it's going to give a different type of product, right? So there's the primary position, okay? And as that opens up, what do we have? We have that there, and we have the 2 alkyl groups on there. And after quenching with water, we'll get that. So we just made this bond right here. We get this, okay? And we get the tertiary alcohol. You would not want to draw this product adding at the more hindered side, right? Because that would open up like this and give this product, okay? That would be harder to attack there because you'd have to hit the back side of the sigma star getting past these 3 alkyl groups, right? So that's tertiary position. This is a primary position. And so you could say it's SN2-like, okay? So selectivity-wise, not that one, not the more hindered one, but this one here adding at the less hindered position, okay? So sometimes we have a choice on those. All right, let's see. Let's wrap up with cuprates real quick. I'll show you Victor's picture. And on Friday here, we're going to do some multi-step things, and we'll review all these reactions. So we'll still be working on Chapter 20 on Friday. But let's see here the cuprates adding to enones, okay? And when we say enone, that's kind of a funny looking word. No, not Ewok, or it's not some Star Wars character, enone. It almost sounds like that. It's a contraction of alkene, ketone. And here it is, ketone, alkene. And they have to be conjugated to each other, okay? And cuprates are very good at this. So let's look at diethyl cuprate here. And the diethyl cuprate has 2 alkyl groups on it and a negative charge, and the lithium is a +1 charge, being an alkali metal, right? So this is the true structure of this. And let me give you the bottom line here on the product. The product will be a ketone, but that alkyl group from the cuprate will be at this beta position. And this alpha beta designation is just how many carbons away from the carbonyl group, okay? So the beta position will get the alkyl. The alpha position will get another hydrogen. So our mechanism has to account for that. And the reactivity is such that, well, even if we had excess cuprate, look, we're not adding to the ketone here. We're just adding to the enone. And at the beta position, after all, too. Like I said, these are milder reagents. So we'll have to account for that attenuated reactivity. But what can we do here? Well, let's have one of our alkyl groups come off and add to this position and push the electrons all the way through the conjugation system of the enone, okay, like that. And so what do we get? We'll get O minus. We'll get the double bond moved over right there, and we get the ethyl group there, okay? And notice we'll have the lithium cation still there. And what about the copper? The copper ends up as just ethyl copper. Cuprate has 2 alkyl groups. This is just ethyl copper. And again, this is a late transition metal, copper 1 oxidation state. And that's really the end of the road for the copper at that point. But you have the lithium, you know, the countercation here for this structure. What are we going to call this? See, we have an alkene and an O minus. It's an alkoxyalkene. We're going to call this an enolate. 8 meaning charged, enol, meaning what? Alkene alcohol that's lost its proton. So this is an enol that's ionized. It's called an enolate. And it's just a consequence of pushing the electrons here and then up onto the more electronegative oxygen. Why? How come we didn't just add this directly to the carbonyl? Well, like I said, it's a milder reagent, so it needs to add in such a way that it gives a more stable anion. We could add here, and think about this, right? And if we added there, we'd get what? The ethyl group just adding right there, and O minus there. These are both O minuses, right? We've been doing all these O minuses before with the Grignard reagents. This is a different O minus though, right? It's conjugated to the alkene. We call it an enolate. Why? It's resonance stabilized. This is a less reactive organometallic. It needs a more stable intermediate, the enolate. So it dumps its nucleophile to the beta position to give the more stable enolate. This pathway is lower in energy for these less reactive organometallics. Well, how do we get to the product though? Let's see. Well, when we dump in water, what do we get here? Here's water. Bring the pair of electrons down from oxygen and protonate now at the alpha position. Yeah, and that will give us the second hydrogen there from water, okay? So you can see this came from the cuprate, the dialkyl copper, delivered one alkyl group beta position. We have the stabilized, the lower energy, conjugated resonance stabilized O minus, being an enolate. We could draw another resonance structure here, right? Forming a carbonyl and having what? A carbanion, negative charge. In fact, let's do that. What's that resonance structure look like for that? Again, double-headed arrow there. What would that look like? Well, we'd reform the ketone, but you see we'd have the negative charge here now, right? Verify that's the resonance structure of the enolate. And so what? This can also grab the proton from water. You can use either resonance structure to get to the product, okay? But with cuprates, they're less reactive because it's a late transition metal, and we have to go with that. Okay, I think that covers all the topics, actually. We'll do multi-step synthesis and some planning. Oh, and the protecting groups next time. So we got a few things. We'll do some more epoxide reactions, more cuprates. We can have a lot of fun here with synthesis now with all these other agents. Let's go back up to the overhead here. See, oh, there you go, Victor Grignard. Very impressive mustache. Won the Nobel Prize in 1912, over 100 years ago. He shared the prize with Sabatier, another famous French chemist. What reaction did Sabatier work on? Hydrogenation. We've been covering his reactions all along. We never use his name. We always use the term hydrogenation. It's more descriptive. But I think the Grignard reagents, because of the mustache, are more important that way to use his name. No, it's the versatility and making carbon-carbon bonds, which makes things more useful, you could say. And what about solvents? So I pointed out solvents in a couple of cases here. THF, there it is. You see it's still pretty polar, has a high enough dielectric constant, dipole moment. It's infinitely soluble in water, but it's aprotic. So it's able to solvate a lot of organic compounds and bring them into reactions there. You don't want to use water, H2O, even though it's more polar and everything. That's a proton source. So we don't use alcohols or water for the Grignard reagents, okay? But these guys here are two non-polar. You can't use those. Electrostatic potential energy maps, you can see that these are useful. The red coloring here is high electron density. The blue or greener thing is lower electron density. So the polarization here of methyl chloride, you see the red side is the chloride, and then the blue side is the methyl group. And that's for SN2, right? And those type of reactions there. But what we're looking at now are the organometallics. The lithium, you see, is the blue part, and then the redder part is the methyl anion in this case, right? So the positive side here, where there's a dearth, a lacking of electron density, is what's becoming the cation there, the methyl, the lithium plus, sorry. And we could do the same analysis for a Grignard there, but we see we've reversed the polarity. Blue from red, and what? Blue now to reddish orange. We've reversed the polarity there. So yeah, stay tuned for Friday. We'll finish up chapter 20. Your quiz 4, though, is due tomorrow. So stay tuned for that and be reading ahead into 21. We'll continue then. So very good. We'll see you next time. Thank you.